So Holger will be telling us about silicon nanotechnology, and they're developing some very nice work at Fraunhofer IWS on columnar silicon anodes. So the stage is yours, and yeah, I wish you good luck.
Thank you very much. Yes, so I'm going to talk about the silicon anodes for high energy lithium-ion and solid state battery cells. This is work we do at Fraunhofer IWS as part of the Advanced Battery Technology Center, an R&D center where we aim to combine expertise in advanced cell chemistry, innovations in electrode processing, and customized cell prototyping. So the idea is to look at new materials, new processes, and implement them into application-relevant multi-layer pouch cells for evaluation. And this is what we do for silicon as well. We are especially interested in silicon thin films, which contain no other components than silicon, so 100% silicon, we call it. This is columnar films directly deposited on copper substrates, on current collectors. And with this, we can utilize the full capacity of the silicon. And with this, we obtain much higher specific capacity, both in terms of volumetric but also gravimetric capacity when compared to graphite. And this boosts energy density, gravimetric and volumetric on cell level when compared to lithium-ion batteries. We use a quite simple approach based on physical vapor deposition. This is a vacuum deposition technique where we grow the silicon on roughened or dendritic copper foils. And due to the rough surface of the copper, we obtain columnar silicon structures, as you see in the SEM image on the bottom. And this can be done on a small scale in our laboratories, but it also has been demonstrated to be scalable to roll-to-roll equipment on 500 millimeter widths together with our partners from Fraunhofer FEP. The main challenge of silicon, as we mentioned today already, is volume expansion upon lithiation. This is also happening in our films, and this induces a high stress in our films. And we spent quite some work on identifying possible solutions or compensation for this stress induced during lithiation. We worked on microstructuring these films, but also on the role of the substrate, and this is shown here on the photographs on the bottom right. You see two examples of silicon films being used in coin cells, where in one cell we used a current collector with 10 micrometer thickness, the other of 80 micrometer thickness. This is just an example to show that the mechanical strength of the foil can avoid the wrinkling and the deformation we see for the 10 micrometer foil. Just when we go to a more stable and a bit thicker current collector, we can avoid this, and we can observe the stabilization and effective suppression of the deformation effect in the height measurements upon inoperando cell testing. So we monitor the thickness of the cells during cycling, and with the black curve we see a more or less uncontrolled thickness increase. This is due to the deformation effect, which we can avoid in the other case. So we carefully look at this by online monitoring of all our pouch cells. So based on this experience, we built multi-layer pouch cells and used 100% silicon anodes, double-side coated, together with NCM 811 high energy cathodes provided by our partners from Fraunhofer IWS. And these multi-layer pouch cells have been built and tested with reasonable areal capacity. So it's aiming to demonstrate relatively high energy density. So these cells obtained almost 1,000 watt-hours per liter with a high first cycle Coulombic efficiency of 87.8%, which is without any pre-lithiation. This could possibly further boost the cycle life and the first cycle efficiency, or compensate the losses which we here still have. But still, we obtain reversible cycling on a high energy cell based on our concept on cells